The agent receives a single sparse reward, only at the absolute end of a massive chain of decision. Large language models are increasingly operating autonomously over long horizons. They execute multi-turn interactions, navigate tools, and process environment feedback to solve complex problems step by step. To train these models towards specific goals, engineers rely on outcome-based reinforcement learning, or RAL. Outcome-based RAL operates on a simple logic: let the agent try and grade its final result. But this creates a severe structural problem. This diagram visualizes the resulting retroactive blind spot. You can see the trajectory unfold across dozens of intermediate actions, concluding in a final evaluation of success or failure. Because the grade is final, the model registers the outcome but receives zero token-level guidance on which intermediate choice drove that result. This is the supervision gap, the vast distance between the episode-level outcome and the learning required at each dark node. Without precise token-level guidance, scaling agentic behavior hits a wall of trial-and-error inefficiency. The model is essentially guessing which of its past actions worked. Until an agent can isolate and evaluate its own intermediate steps, its capacity for true autonomous reasoning remains stalled. To bridge this gap, researchers developed SEED, self-evolving on-policy distillation. The core premise of SEED is introverted analysis. It forces the agent to mine its own completed on-policy trajectories to manufacture its own training signals. In Phase 1, the policy model becomes a trajectory analyzer, examining both its wins and losses after a finished task. This creates a highly efficient architecture. The exact same policy model that acts in the environment serves as the engine analyzing the resulting data. The analyzer reviews the action chain and extracts natural language rules, referred to in the research as Hindsight Skills. These Hindsight Skills fall into specific actionable categories. The model generates reusable workflows for efficient multi-step actions, flags decisive observations that turned the tide of a task, and maps out failure avoidance rules to prevent repeating errors. For example, after a multi-turn software coding error, the agent might extract a rule like verify the imported library version before compiling dependencies. These extracted rules give the model a high-level semantic understanding of exactly what went right or wrong deep within the task chain. Phase 1 effectively turns raw outcome data into structured text, but text alone cannot train a neural network. The system must now mathematically inject this natural language back into the agent's probability weights. This injection occurs in Phase 2, where SEED converts the generated Hindsight Skills into a mathematical distillation signal. To do this, the system performs a process called rescoring. First, the policy model evaluates its past actions strictly under the ordinary context, meaning no hindsight rule is applied. This visualizes that ordinary context. The heat map on the left shows the model's baseline probability distribution, how likely it was to choose specific actions before it learned anything new. Next, the model reevaluates those exact same actions, this time augmented with the newly generated hindsight skill. Including this skill forces the action probabilities to shift, naturally weighting the correct choices higher. By comparing these two states, the researchers isolate the delta, the exact probability shift between the ordinary context and the skill-augmented context. Calculating this difference isolates the precise mathematical influence of the text-based hindsight skill. That isolated shift is the ultimate target. It provides a dense, token-level on-policy distillation signal manufactured entirely by the agent itself. With the distillation signal mapped, the model applies it during the actual training loop. SEED utilizes joint optimization. The newly generated dense token-level signal is optimized simultaneously alongside the sparse outcome-based reward. This solves the original supervision gap. The agent now maps the macro reward directly down to the micro actions. In standard RL, the agent would blindly guess its intermediate steps in the next training epoch. Here, the dense signal explicitly guides the intermediate tokens, preventing the model from repeating localized, hidden errors buried deep within a multi-turn task. And critically, this highly specific guidance requires zero human-annotated step-by-step data. Joint optimization anchors the agent's ultimate objective to the granular mechanical steps of how to achieve it. The self-evolving prefix of the SEED framework isolates why this specific architecture is necessary for advanced agents. The standard alternative in machine learning is to use a static external teacher model to provide distillation signals to a smaller student agent. Static teachers create a scaling flaw. As the student agent trains and improves, its policy shifts out of distribution. It eventually encounters complex states the static teacher does not understand, and the training signal degrades. Seed bypasses this degradation completely because the current policy is acting as both the actor and the analyzer. Whenever the policy updates its weights to make better decisions, its capacity to analyze its own hindsight updates simultaneously. Encountering new operational complexities and failure modes, the agent instantly analyzes them at its current intelligence level, generating appropriate hindsight rules to adapt. A self-evolving loop ensures the supervision signal never misaligns with the agent's current capabilities. Moving from the theoretical architecture to actual testing, the seed framework yields distinct empirical results. The primary output is a massive, measurable improvement in sample efficiency compared to using outcome-based RL alone. Because the model extracts maximum value from every action, it requires far fewer full trajectories to master a complex task. Tests demonstrate robust generalization, with the model successfully applying its learned hindsight skills to entirely unseen operational scenarios. The architecture is also not limited to language models. In testing, Seed proved highly effective across both text-based reasoning arrays and vision-based agentic tasks. Self-evolving on-policy distillation elevates general agentic reasoning across multiple modalities. An agent that can bootstrap its own learning forces us to reconsider the timeline of AI development. The reliance on slow, expensive human step-by-step annotation is no longer a hard ceiling for capability. If models can systematically isolate their own decisive observations and mathematically correct their own failure rules, the question is simply, what are the theoretical limits of a machine that serves as its own perfectly aligned teacher? From research paper to working prototype, this is Syntheic Labs.